Okay, this is part 2 of the lesson 5 on radioactive elements. We're going to talk right now, what does radioactive decay produce? So remember, when radioactive elements are left for a time, they will begin to give off energy and particles. We're going to look at the different particles that they give off. We talked about how unstable isotopes, which is just a change in the nucleus, can create an unstable element, and also how radioactive elements can over time become different elements because they basically break down, is what you want to know. So we're going to look at figure 3 here for just a second. There are 3 different types of particles that are produced in radioactive decay. Figure 3, the very first one, starts and it says alpha decaying. That's the not the very first type of particle. It's the one that we're going to talk about first. So an alpha particle consists of 2 protons and 2 neutrons. It's going to be positively charged because, of course, there are only 2 positive charges within it. So basically what you want to think of is that here is the nucleus of any certain element. Remember, the electron cloud is on the outside. When you leave that atom for a short period of time, or even just depending upon the atom, it could be a long period of time, it's going to give off particles. When it gives off this alpha particle, that alpha particle is going to consist of 2 protons and 2 neutrons. Okay, so that particle is going to be positively charged. So the release of the alpha particle by an atom during this alpha decay, it's going to decrease the atomic number of this particle. Atomic number decreases. When that happens, it's going to decrease the atomic number by 2 and the mass by 4, or technically the mass number by 4. When it does that, it's going to become a different element. So just to give you an example here, they tell you that thorium, which is 232, is going to decay and produce an alpha particle. When it does that, the thorium is now radium-228. It's not the particle that it's giving off. It's the actual starting atom. It just gives off 2 protons and 2 neutrons. And when those 2 protons and neutrons leave, that original particle is now a different element, in this case radium. So the beta decay is going to be, it's going to change into a negatively charged beta particle and a proton. So a beta particle is a fast-moving electron given off by a nucleus of the radioactive decay. The new proton remains inside the nucleus, and the nucleus is then left with 1 less neutron and 1 more proton. Its mass number remains the same, but its atomic number increases by 1. So, for example, carbon-14's nucleus is going to decay to produce a beta particle. Okay, a beta particle. Here's that beta particle there. And a nitrogen-14 nucleus. So to help them make this a little bit more understandable, 1 proton is going to be gained in the nucleus. Okay, it's going to gain a proton. And 1 neutron is going to be lost. Gamma radiation, one thing that you want to know is that alpha and beta decay at almost always accompanied by a gamma radiation as well. So gamma rays consist of high energy waves. These are similar to X-rays. Gamma rays, also called gamma radiation, have no charge and do not cause a change in either the atomic mass or the atomic number. So in this case, it's just going to give off the rays. There's not going to be any protons gained or lost, or neutrons either. So what you kind of want to think is that it's just giving off a high energy wave. That's what it's going to do. It's going to give off that wave. So what are the effects of nuclear radiation? Figure 4 depicts a radioactive source that emits alpha particles, beta particles, and gamma particles. Alpha particles move very fast. They can be blocked by just a sheet of paper. So these block alpha. Alpha radiation can cause an injury to human skin. It's going to be kind of like a bad burn. Beta particles are much faster and they penetrate more than alpha particles. They can pass through paper. So let's just do this. Let's say that here's our alpha particles, and the alpha is going to stop at the paper, but beta is going to continue on. Okay, so beta particles continue on. They can pass through the paper, but they are going to be blocked by an aluminum sheet. That aluminum sheet needs to be 5 millimeters thick. Beta particles can also travel into the human body and damage its cells. Gamma radiation is going to be the most penetrating. You would need a piece of lead several centimeters thick or a concrete wall about a meter thick to stop gamma rays. So gamma rays are going to go through here and they're going to stop. They can pass right through a human body. Gamma rays deliver intense energy to cells and can cause severe damage, which is the reason why you hear a lot of sci-fi using the term gamma rays, because it's going to be the worst out of all three. So what is the name of a particle produced by radio decay that consists of 2 protons and 2 neutrons? That is going to be an alpha particle. The 1, 2, 2, 1 B to rank the most penetrating to the least penetrating. We know that just looking at this picture up here, that the alpha particles are going to be the least penetrating. The gamma is going to be the most penetrating, and so that means that beta is going to be right in the middle. What are the identity and mass number of a nucleus formed during the beta decay of magnesium 28? Okay, so what you want to look at when you're looking at this type of radioactive decay, you want to look at magnesium, which they're saying is a 28. Your final number is still going to be a 28. We just need to figure out what element is going to go in there. The atomic number of magnesium is 12. So the atomic number of magnesium is 12. Well, according to beta rays, it is going to gain 1 proton. When it gains 1 proton, the atomic number goes from 12 to now 13 because it's gained 1. What you want to do is find on the periodic table the element that has the atomic number of 13, which in this case is going to be aluminum, and you are going to put that into that answer. So your answer is going to be aluminum 28. Sorry. Okay. So aluminum 28 is going to be the answer to that. How are radioactive isotopes useful? Radioactive isotopes have many uses in science and industry. The energy released by the isotopes is going to be useful in itself. So uses are going to include determining the age of fossils, tracing the steps of chemical reactions, industrial processes, diagnosing and treating diseases, and also to provide sources of energy. We've actually found in recent years that in terms of dating, that uranium is becoming much more useful and much more effective than carbon dating is. So it's very interesting. If you look, they're able to go farther back with uranium dating than carbon dating, and it's, like I said, a little bit more precise. So the half-life of a radioactive isotope is the length of time needed for half of the atom in the sample to decay. So if I have an atom here, we are going to find out the amount of time it takes for half of that atom to decay. So the half-life is going to be different from each radioactive isotope. So the half-life of carbon is going to be much different than the half-life of uranium. And since uranium has a much higher atomic number, then that means that you can date even further because you're going to be able to decrease by half, decrease by half, decrease by half without running out of that particular atom. So carbon dating is effective for smaller amounts of time dating, but if you're talking about earth science, understanding geology, understanding fossils, uranium dating is going to be a little bit more effective. Fossil of traces of remains of living things have been preserved for fossils millions or billions of years. We are able to use these half-lives to date some of them. Uranium, like I said, is going to be much more effective. For younger fossils, they're going to use the carbon-14 because it's not going to have as many half-lives, so it's going to be more useful for smaller amounts of time. So as plants grow, they use carbon dioxide from the air, right? We know that. We've known that for a few years now. A fraction of all carbon dioxide contains the radioactive isotope carbon-14. This becomes part of the plant's structure. After the plant dies, it stops taking in carbon dioxide. If the plant's remains are preserved, then that means that the carbon-14 is going to start decaying or breaking down over time. Scientists can measure the amount of time based on the half-lives. So scientists can calculate how many half-lives have passed since the plant died. That gives them an estimation. It's not an exact, it's just an estimation. This is called radioactive dating. I would like to spend some time on the do the math, but I would really like for us to look at that individually so we can break down the table and do a little bit of calculation. So it's okay if at this time you want to go ahead and skip. Now for the third video, we're going to be talking about uses in science and industry, medicine, and nuclear energy. So if you want to stop now and you want to go to the number 3 recording, you can do that at this time.